In this video, we'll look at buffers to see why they're useful, and then we'll see how they work. Before we talk about buffers, we should go over some examples of places where we can find them. In our bodies, we can find buffers, for example, in our blood and in our stomach. And in aquatic environments like a fish tank, there should also be a buffer included too. Buffers exist because living systems operate in a pretty narrow range of pH. For example, in our blood, the pH range should be slightly basic between 7.2 and 7.6. If blood pH goes out of this range, then this could lead to some health problems such as drowsiness, confusion, and it can even cause tremors in our muscles. One way to keep the body's pH in this range or in a stable range is by having a substance in our blood called buffer. There are different types of buffering substances in different parts of the body and also in different places, such as a fish tank or a swimming pool. Formally defined, a buffer is a weak acid or a weak base solution that resists changes in pH. Let's take a look at a buffer in action in this short video below. There's water on the right-hand side and buffer on the left. There's also acetic acid on the left. In each of these test tubes, the demonstrator is going to be adding NaOH, which is a very, very strong base. But he's only going to be adding it little by little. But before that, he's going to add a pH indicator. So I'm going to start the video now. So he's adding a pH indicator. And before he adds the base, just take a look at the colors. The water is slightly yellow, the buffer is a little bit orange, and the acetic acid is red. As he's adding the strong base, the NaOH, it should start shifting it towards the purple spectrum, the purple part of the spectrum, because it is a strong base. And look what happens. So he's only adding like 1 or 2 drops to each test tube right now. So notice, I'm going to pause the video. The water is already purple. It's already considered a high pH. The buffer and the acetic acid, however, they're the same color, meaning their pH didn't change. So I'm going to start the video again. Now he's going to be adding more and more of that strong base into the buffer and the acetic acid. So it's actually taking a lot more. And there he goes. He's adding even more of the strong base. Notice that the acetic acid is starting to change colors already. And the acetic acid is pretty much the same color as the buffer. But look, the acetic acid is turning purple, right? So the acetic acid is already turning purple, and the buffer is the same orangish color that it started off with. Now, what that means is, if the buffer is the same color, then that means the addition of the strong base didn't cause the pH of the buffer to change. The pH of the buffer is pretty much the same. So buffers are important because they resist pH changes. They resist it really well, which is important for living systems because living systems must operate at a very narrow range of pH. So if you have a buffer in a living system, that'll keep the pH range to be pretty much the same, and then everything will function normally. Different systems, whether we're talking about living systems or in a chemical lab, they use different buffers. And there's many, many different buffers to choose from. For the video example that we just saw, the buffer color, if you recall the color, it was orangish. Now, in this list, something that would be in the orangish range is something called bis-tris buffer, which is used to keep the pH of a chemical system around 5.8 to 7.2, which would be orangish based on the pH indicator that was used in that video. The key idea, however, is that there's a whole bunch of chemical buffers that can be used to buffer specific pH ranges. So depending on which pH range that you want to keep your solution at, there's likely a list of a selection of buffers that you can pick from. You'll likely pick the buffer that's going to buffer at the correct range that costs less. That's basically cheaper. So there are a lot of buffers to choose from, and the ones in this list, they're artificially created. But even though there are artificial buffers, there are the ones that are in our bodies that are natural. All right, so there's naturally occurring buffers in actual living organisms. Now we can get to the fun part of learning about how a buffer works. So let's look at an example for the bis-tris buffer in a beaker. You'll notice that there's a couple different molecules in the beaker. The bis-tris buffer is actually an equilibrium system of a weak acid. That means that there's a weak acid, HA, in the beaker, and it's only partially dissociated into its H plus ions and A minus ions. Since it's partially dissolved, this explains why there's a double arrow. There's also water in this beaker. The bis-tris solutions usually have a pH around 6. What happens if we start adding strong acid into this buffer? In other words, what happens if we add H plus ions? If we add H plus ions, then you might think that the pH will go down, because H plus is acid, pH should go down, right? But this is actually what happens. So look carefully what happens. The H plus ions combine with the A minus ion in the solution, and then they turn into the weak acid molecule, the HA. So watch this again. So as soon as the H plus is added to the solution, they're actually used up. That means that the pH will not drop. This is actually Le Chatelier's principle in action. So look at the equilibrium equation below, and I'll explain it to you in that way. If we increase the amount of protons, or the H plus ions, there'd be too much product, and the equilibrium doesn't like this stress. The stress to this equilibrium will cause the equilibrium to shift to the reverse direction, and this means that the H plus ion is going to be used up so that it creates more of the weak acid molecules. We can sum this up into a key idea right here. When adding a strong acid to a buffer, the additional H plus ions combine with A minus ions. Therefore, the solution doesn't become more acidic. Now let's look at the same buffer if we added a strong base instead. When you add a strong base, that means we're adding hydroxide ions. You'd think the pH would go up, but this is actually what happens, so look carefully. So the hydroxide ion combines with the H plus ion in solution, and then it forms water. But then an HA molecule that's in the solution dissociates to form the H plus ion back again. Let's see this one more time. If you were to look at the equilibrium equation on the bottom, we could explain this with Le Chatelier's principle again. When we add base into a buffer, the hydroxide ions from the base will combine with the protons from the solution to form water. That means the amount of H plus ions will decrease, and this is a stress to the equilibrium system. This would make it so that there's less product. And in order to undo the stress, according to Le Chatelier's principle, the system will shift in the forward direction to recreate or remake the H plus ions. Therefore, the pH will not change since the concentration of the H plus ions doesn't change. To sum this up, when adding a strong base to a buffer, the additional hydroxide ions combine with the H plus ions to form water. This temporarily lowers the H plus ion concentration, but due to the Le Chatelier's principle, the H plus ions will be reproduced again from the HA in the buffer. Therefore, the solution doesn't become basic. There's one last term I want to go over. This term is relevant in answering the question above. Do buffers buffer forever? The answer? No. There's something called buffer capacity. This is the extent to which a buffer can resist pH changes. Below there's two beakers. The beaker on the left has a higher buffer capacity than the right beaker. Both beakers have bis-tris buffer, but there's something different about them. The difference is the amount or concentration of bis-tris molecules. The one on the left, the one with the higher buffer capacity, has more bistress molecules. So I'm going to remove the hydrogen or the water molecules so that you can see that the one on the left has more of the bistress molecules. If you are able to follow along with the explanation of how a buffer works, then you should be able to understand why having more buffer molecules will give you a higher buffer capacity. Here's the key idea. If there's more buffer molecules or ions, then the solution will have a higher buffer capacity. I hope this video helped.